There is a vertical cylinder of curved metal blades spinning in a suburban backyard right now, generating electricity from wind too faint to feel. No dramatic gusts, no hilltop, no open plain. The air moving past it sits around 2 to 3 miles per hour, below what most people notice on their skin. A conventional wind turbine would register that as nothing. It would sit motionless. But this rotor is already turning, already feeding current into a battery, already doing work from air the modern wind industry has officially decided does not count. You can build or source a unit like this for a few $100s. It needs no tall tower, no professional crew, no yaw mechanism that chases wind direction, no electronic governor that shuts it down in a storm. And despite measurable performance advantages in the exact wind conditions that exist in most suburban neighborhoods, turbulent, low speed, constantly shifting air above rooftops and garden fences, this design is almost entirely absent from mainstream energy programs, contractor catalogs, and subsidy lists. What is it? How does it harvest power nobody else can reach? And why is it not on every rooftop? The answer begins on the Persian Plateau, more than 1,000 years ago. Flat terrain, unreliable wind direction, grain to grind, water to lift, no engine. The people who built there faced a specific problem. Wind on flat land does not blow steadily from one direction. It shifts and gusts and rotates through the day. A horizontal windmill, the kind that must face the wind directly, is nearly useless under those conditions. You would spend more time rotating the mill than grinding grain. So Persian engineers built something different. Vertical sail panels mounted around a vertical central shaft, turning a rotor that could catch wind from any direction at once. It did not need to face the wind because it accepted all of it simultaneously. This was the Panemone windmill, likely the first practical wind machine in human history. Its design logic was not mystical. It was the correct engineering response to a real physical problem. That vertical axis logic spread. Medieval builders in China and early modern Europe applied it for water pumping in sheltered valleys where directional mills could not be correctly positioned. The principle kept reappearing wherever wind was inconsistent and necessity was high. Then, in the 1920s, two engineers refined it into forms that still exist today. French engineer Georges Darrieus patented a curved blade vertical rotor designed to harvest low-speed wind through aerodynamic lift rather than pure drag. Finnish engineer Sigurd Savonius developed a scooped cup rotor that begins spinning at nearly zero wind speed and accepts air from every direction simultaneously. These were practical answers to the oldest wind problem. What do you build when the wind refuses to cooperate with your machine? The question now is whether these designs actually work where most people live. That question has been tested. Researchers measuring real wind profiles above suburban rooftops in the UK, the United States, and the Netherlands found that rooftop and garden-level wind is turbulent, multidirectional, and constantly shifting, precisely the profile that small horizontal turbines handle worst. A horizontal turbine must face the wind precisely, and in turbulent suburban air, its yaw mechanism is continuously hunting, correcting, and stalling. It spends much of its time misaligned. Engineers at companies like Windside in Finland, alongside urban wind researchers, concluded that residential horizontal turbine underperformance was not a power density problem. It was a mismatch between machine design and real-world wind character. Vertical axis units tested at roof edges and garden positions produced consistent output at 3 to 6 miles per hour of turbulent wind, conditions where horizontal units of comparable price simply stalled. Understanding why requires looking at how each design actually works. A Savonius rotor operates on drag. The curved scoop catches pressure on its concave face and turns. The opposite blade simultaneously presents a narrower profile to the returning wind, so the net force is always rotational. Wind physically pushes the blade. Even the lightest breath of air exerts force on that concave surface. The rotor cannot remain still in moving air. Cut-in speed sits around 1.5 to 2 miles per hour. A Darrieus rotor works differently. Its curved aerofoil blades do not rely on being pushed. They generate aerodynamic lift as air flows across their outer face, exactly as an airplane wing generates upward force. The blade is pulled forward by low pressure on its curved surface. Once spinning, this lift accelerates the blade beyond the wind speed itself, a relationship called tip-speed ratio. The Darrieus extracts energy efficiently from gentle airflow by generating motion faster than the wind driving it. Because it needs a small push to start, hybrid designs pair a Savonius core with Darrieus blades for efficient running. But the geometry carries a deeper advantage. A vertical axis rotor presents the same profile to wind arriving from any compass direction. Turbulence becomes structurally irrelevant. Wind shifting from southwest to northwest in 3 seconds does not interrupt the rotor at all. For a horizontal turbine, that same shift is a mechanical problem requiring active correction. In a city or a suburb where built structures deflect and scramble airflow constantly, this is not a minor difference. It is the difference between a machine that runs and one that hunts. Then there is capacity factor, the percentage of time a turbine actually produces power. A horizontal unit rated at 400 watts that runs 15% of the time delivers less usable energy than a 200-watt vertical axis unit running 60% of the time. Rooftop horizontal turbine installations in UK residential areas routinely produced 50 to 80% below manufacturer estimates. Vertical axis units in comparable positions met or exceeded theirs. For someone off-grid or supplementing grid power, that consistent trickle across LED lighting, phone charging, and a router is genuinely useful, and it arrives quietly. A low, even hum, rather than rhythmic blade noise, with no storm shutdown drama. You can watch the blades moving in air you cannot feel, which creates the strange impression of energy being pulled from nothing. So why is nobody selling you one? Start with the honest limitation. Vertical axis designs have lower peak efficiency than horizontal turbines in strong, steady, elevated wind. On a coastal hilltop with consistent 12 miles per hour of airflow, horizontal turbines generate more energy per dollar of rated capacity. Some large Darrieus installations in the 1980s developed fatigue and resonance problems at industrial scale that gave the entire category a lasting reputation problem, even though small residential units face none of those structural stresses. But that limitation alone does not explain the absence. Subsidy and certification frameworks in most countries were written specifically around large horizontal axis turbines. Small vertical axis units frequently fall outside clean energy credit categories or face unclear permitting. The wind industry's installer networks, training programs, and supply chains are organized entirely around horizontal designs. Contractors sell what they can install and service. Vertical axis units offer little recurring revenue, simple geometry, few moving parts, no annual filter replacement, no proprietary service contract, no branded component cycle. Insurers and inspectors prefer what they recognize. Developers select certified standard products. Homeowners are never offered an alternative because it does not exist in the catalog the contractor is working from. Energy comparison tools measure rated peak output, exactly the metric that flatters horizontal designs and obscures vertical axis real-world advantages most completely. The system rewards the wrong measurement. Reclaiming the principle requires attention to geometry. Blade curvature matched to rotor diameter is not decorative. It determines how efficiently the rotor harvests drag and lift. Cheap hub bearings introduce friction that kills low-wind start performance, which is the core advantage. Mounting too close to a wall creates a turbulent dead zone that defeats the purpose. Oversizing the generator relative to the rotor introduces resistance that prevents starting in light wind exactly when you need it most. Get those details right. And even a modest unit producing 20 to 50 watts continuously in an average wind of 3 to 5 miles per hour has practical value. Open-source fabrication communities, small specialist manufacturers, off-grid engineering networks, and permaculture groups have kept these designs alive. They pair cleanly with a battery bank and charge controller, and they complement solar in climates where winter wind outlasts winter sun. The vertical axis turbine is not a hobbyist curiosity. It is a legitimate wind harvesting architecture that outperforms the dominant design in real-world residential conditions. And it was sidelined not because it failed, but because it could not be profitably standardized, financed, serviced, and sold through the structures the modern energy industry built around a different machine. Every time a solution disappears for economic reasons rather than technical ones, something genuinely useful is lost. The question worth sitting with is how many other principles were quietly shelved for the same reason, and whether we can recognize them before they vanish entirely. If a vertical rotor can harvest energy from wind too faint to feel, what about a device that generates electricity from the temperature difference between night air and the ground? No moving parts, no wind required, complete silence. That principle exists. It was understood long before any grid was built, and almost nobody is offering it to you either.